All right. Hi, my name is Roland Bock. I'm Principal Software Engineer at PPro Financial Limited. I'm the author of SQL++ 11 and some other libraries, and I'm here to talk to you about how to test static assert. I'm going to use some examples from SQL++ 11, so I'll start with that so that you have an idea of what that is. So SQL++ 11 is an embedded domain-specific language for SQL and C++, which means that you can express SQL queries as C++ statements, and then the compiler can tell you if you're doing everything right or maybe you're doing something wrong. So for instance, it can check whether all the columns that you select are connected to tables that you have in the from in a select statement, or it can test whether you're comparing apples and oranges and so on. So it's very different from what you have if you have a string-based approach and you just write a string with your SQL statement. And this is one example. So here we have an update statement. So we want to update a table called tab. We want to set the column name to John Doe. That looks innocent enough, but if you compile this with Clang, it gives you an error message because the library says, well, if you have this update statement, it doesn't contain a condition, right? That is likely an error. So if you don't have a condition, you should either write that you explicitly don't want to have a condition and you want to update everything, that's fine, or you should write a condition, but you should state what you want, and the library here complains that you didn't explicitly state what you want. So it says it's an error, and there is a static assert that fails with this red error message saying that, well, you should either call where or the function unconditionally in order to say what you want. Okay? And that is cool. That's very, very helpful because if you want to use this library, it's good to have these handwritten error messages, and that's what static assert is for. You can test at compile time, and you can test for certain conditions. It produces a hard compile time error, so there is no recovery from that, and it yields handwritten error messages. That is exactly what you want in some situations. Good. But of course, it's only cool if you get everything right. If the static assert is somehow not exactly right, with the condition maybe being wrong or the message being wrong, then you have a problem. Then I received an issue for one of the connector libraries of SQL++ 11. It was earlier this year, which said that if you compile the same code with MSVC, you will get just with this error message. It's the only thing that you get. It just says, well, a variable cannot have the type void. Okay, I mean, that's true. Okay, but it is extremely unhelpful because the compiler is correct to do so. It's not very helpful, but the compiler is correct to do so because the return type of this function in this case when there is an error is actually void. Other compilers do that too, but the compiler is allowed to just give you one error message, even if there are tons of errors. It's allowed to just give you one error message. In this case, the MSVC decides to just tell you, well, the return type is void. You cannot assign that to some variable. That's your problem, and it doesn't go into the function and actually run into the static assert. So. It's annoying, but it's standard conforming, so somehow, yeah, we have to deal with that too. Okay, so static assert is cool for all the reasons I already mentioned, but sometimes you might get the conditions wrong. Sometimes it just goes missing, and well, it's just not there. Well, and that means it needs to be tested because we need to be sure that it actually fires when it should. Right, so that's the goal for today. I want to assert that all my static asserts actually fire when they should. Okay, good. And yeah, MSVC uses, so if for some reason it still gets lost, then I still want to give them some information that helps them to understand what the hell is going on. All right. There are some basic approaches. So, for instance, if you go to Stack Overflow and ask, how can you test static assert, then you will get interesting answers like code staring, which is actually what most people do. Whenever I talk to people about how they test their static assert, most of the time, the answer is, yeah, code staring. We just look at it and see, well, if it's correct or not. I have about 60 static asserts in my code, so code staring, well, works for, I don't know, 1 or 2 maybe, but for 60, I know there are bugs. Right? Other approaches are you could replace it with something in runtime. Okay, that's stupid. So replace static assert with assert. I don't know, that doesn't work. Replace static assert with an exception. You get these answers in Stack Overflow, but yeah, it doesn't work because static assert typically is for something that wouldn't compile anyway. So trying to move that into the runtime, well, not really a good idea. So since it's a compile time error, we can use the build system, of course. So also another suggestion, and I tried that for some time. So you can test it by compiling code, and then you can see whether if you compile something that shouldn't compile, well, it actually doesn't compile, and you get the error message that you expect from the static assert. Right? So I don't know, Daniel Pfeiffer wrote me a CMake code for that, and well, we have this function that takes whatever, basically, you don't have to look into the details. I mean, everybody can write that with some time. But the idea is that you test some code, this max of max in the last line, and give a pattern of the error message that you expect. And then if the compiler fails with this error message, then everything is fine, then the test has succeeded. And well, code could look like this. So we try to take the maximum of a maximum that is not allowed in SQL. So that has to be an error. And well, but as you can see, this already this has a lot of boilerplate code. If you want to test, like I said, several dozens of static asserts and maybe test with 10, 20 conditions per static assert, then this doesn't scale. Right? That's tough. So another suggestion that I heard when I made the proposal for this talk is, well, compiler developers have tools. They have to test static assert themselves, right? So why don't you use those tools? Okay, so Clang has a way to test diagnostic messages, and you can do it like this, and say, okay, I have this code, and you annotate it with these expected node or expected error, stuff like that. And then you compile it with these weird flags, and then if all the comments align with the diagnostic messages of the compiler, everything is fine from the perspective of this command. Okay, so if this compiles without errors, then it's good. Fine. But if you, for instance, use Clang format because this expected comment is just way too long, then it looks like this, and it doesn't compile anymore because the compiler has to have all the messages, all the complete diagnostic messages in one line. Okay, so you cannot use Clang format, so that's ugly. And of course, it depends on the compiler. You cannot use the same test with GCC because they have different tools. You cannot use it with MSVC because they have different tools. I don't even know them. So it depends on the compiler. It depends on the compiler version because the exact error messages depend on which version of the compiler you're using. It depends on compile flags because I don't know what happens if somebody turns on pedantic warnings or so. That's difficult. It very much depends on the setup of the machine that you're compiling on, and yeah, it breaks with modern coding tools. So I don't know. Even if you wanted to use that, because, I mean, these things work. if you have a real-life example, and this is not even real life, but it's getting there. So if you have a function with a static assert in there that tests whether the argument, in this case, is derived from A, and then you call it with something that is certainly not derived from A, you will get something like this with GCC and Clang. It's pretty much the same. First of all, you get the message from the static assert, of course. That's fine. But then the compiler carries on and says, well, you wanted to try t.bar. Int is not a structure, a union, so this won't work. Right? So it carries on. Even though it ran into a static assert, there is no way to recover from a static assert. It still carries on and gives you follow-up messages that you really don't care about. Okay. And also, if you wanted to have multiple test cases in one file, that's going to be ugly, right? So in this case, we have 3 cases that will fire the static assert, 1 case that doesn't. If you try to figure out via pattern matching in the build system or via these diagnostic messages, you have just, I say, no chance. At least for my patients, there is no chance to do that, right? So you have to have 1 file per use case, and then again, it doesn't really scale. Okay. And then there are cases when you have multiple static asserts. I have those in my library. So for instance, in the from clause of a select statement, you first want to test if all the arguments are actually tables. And then you want to test if the table names are unique. Well, there's a good chance, depending on how unique table names is implemented, that this second static assert doesn't even compile, so it's not even firing the static assert because maybe unique table names requires the arguments to be tables. That's a possibility. Or it will definitely yield false if you have non-tables. Any other result would be stupid. So there would be several static assert messages. And again, that would be horrible to maintain in unit tests for these static asserts. Okay. Which means, after this introduction of things that I tried and decided, okay, that's not the way I want to go, we need something else. And first step is to clean up the mess, because as you saw, we have these follow-up messages that we're not really interested in, and some things related to that. So one thing to clean up the mess, or one strategy, is to do tag dispatch. If you have a function, you have a function foo, and you have 2 implementations of that, or two branches of that. One is in the good case, then it does something reasonable, whatever you want it to do in the function, and you have the bad case that you don't even need to implement because it just has to be there to be declared. And then in the function that you actually want to implement, you have then a branch calling this foo impl with a condition of the static assert, for instance. You forward the argument to foo, to the implementation function, and use, in this case, the condition to do the branching. Okay? Okay. So this way, you don't have follow-up errors because you only go into the branch that calls t.bar if everything is fine. Okay? Okay. We also have to take care of the return types, because the return type is not something like void or int or something like that. If it's somehow dependent on the template argument, there's a good chance that this return type will also not compile, will not be reasonable with an invalid type. So in this case, if we have bar, whatever the implementation of bar is, let's say it doesn't compile with int, then, well, this code will still break with horrible error messages in the false case. So it will still carry on after it hit the static assert. So in that case, what you have to do is, well, you have to have some kind of of return type that you use in the bad case. Okay, and then might look like this. You can choose whatever you want basically as a failure type, but it should be something that is not used otherwise. That's why I have this empty struct here called bad statement, and that is used to indicate the failure type, or is used in the failure. Okay, and then we use again the dispatch, and the return type now is, well, is either bar of t or it's bad statement, depending on where you go. Okay. By the way, if you have questions, because it's get more complicated over the way, just raise your hand and ask a question. Okay. So if we use this in code and we call foo7 and just assume that we could do something with the return value, then we will get messages like this. So we don't have the follow-up errors, but we get errors, of course, from trying to use the return type of foo for something that it doesn't have, because bad statement is an empty struct, so you cannot really use that. But otherwise, the messages are quite clean, so you don't get the follow-up errors, so that's good. In MSVC, we see, well, XXX is not a member of bad statement, see declaration of bad statement. Well, thank you very much. So it doesn't give me the static assert. Okay, so, well, we now have constructed the situation that I showed in the very beginning, that, well, we don't see the error message, the real error message that we're interested in. Okay, that's all. And I mean, we still seem to be not much closer to how actually to test static assert. We just cleaned it up a bit. All right. So now let's make static assert testable. So conceptually, what we have to do is we have to test two things. One is we need to make sure that we get the condition right for the static assert. So that has to be isolated somewhere, and it has to be testable somewhere. And we have to make sure that if this condition is true, that the function call somehow contains the static assert. Okay. And the plan is that I came up with is, okay, we actually separate that. So we separate the conditional static assert into two things. One is the condition, and the other one is a type that will always fire the static assert whenever you touch it, basically. Okay, and then we combine that into a function and try to make that testable. Okay, for this small helper, everyone who's seen a talk by me knows this one. So it's a type that has a member that is always false. Only the compiler doesn't know it, because the compiler has to wait until you actually use it in order to figure out whether maybe you have a specialization for this. But for our purposes, it's always false. And then we can wrap the static assert that we just talked about into a type like this. So we have a type name. In this case, well, it's named after the static assert, basically. Assert arg is derived from A. It's the name of the thing, and whenever you construct it with, well, I have a default constructor here. Then whenever you construct it, then the static assert will fire. Okay, because wrong of t, that's always false. Okay, that's one part. We have the counterpart that doesn't do anything, and then we can implement the check. The check can be a conditional. If you have multiple static asserts that you want to combine, you have to, I don't know, chain this somehow, whatever. You can think of that. That's not too hard, but in this case, there's the test is in the conditional, and then if the test is good, then it yields the OK type, and if it's bad, then it yields this static assert type that will always fail. Okay. And then we can do the branching based on this type. So we don't use true type and false type anymore. We use the OK type for the good branch and anything else for the bad branch. And then and this check then has to be our wrapped static assert. Okay. So if we run into the good branch, nothing will happen with static asserts. If we run into the bad branch, the constructor will be called at some time, and then we will definitely have the static assert because it's unconditionally in that type. Okay, so now we have a function that either returns the thing that we wanted to return, or it returns something that will explode as soon as you touch it. Okay, and then we can test it and say, okay, we will try that. So this looks very similar to what we had before, but now we don't have bad statement anymore. We have something that is specific for the static assert. So even if even if the message from the static assert is dropped, at least we have a type name that indicates what the problem is, and that is exactly what's happening. And so if you go and test this with MSVC, at least you get this information. So it's specific for the static assert, okay? Even though the static assert is not there, okay? Okay, and if you ignore the return type and just treat it as a void, then MSVC doesn't have any other chance, and then it will also show the static assert. So everything is good, right? All compilers behave in reasonable ways now. And if we look at the return type, then we see, well, it's a decal type of something. And if we use decal type, and the return type could be this, this thing that explodes as soon as we touch it. But the static assert is only firing if we actually call the function. It is not firing if we analyze it in a non-evaluated context. So for instance, in decal type, which means that we can now test it. We can test static assert by using static assert on the decal type. Okay, so decal type foo of A, that is valid. In this case, it returns void. So we just use std is same and compare that. Okay, everything is fine. And if we call foo with 7, then the return type is this assert arg is derived from A. We compare that with is same, and since we know that this thing would fire the static assert if it were really called, that's the test that we need. Okay, we need to just to test that this is the return type. Okay, makes sense? Okay, cool. And this is what I said basically at CPPCon and in the Munich meetup, and I was convinced that this is all true. It turns out, oh yeah, well, this is just a comment which is, I think it's cool, because, well, just by rearranging the function basically and by tearing apart the static assert in a bit, we can now make it testable. It's really trivial to test. All the tests are not trivial. That were horrible to write before with using the build system. Yeah. Okay. Well, sorry. I rewrote some of the slides very late this week. Okay, so if we apply all this in SQL ++11, it still looks good. So we have this message from the static assert, and we also get this type information, and with MSVC, funny enough, they now show the static assert, by the way. And I'm not really sure what the logic is, but there has to be some logic. So now they show the static assert, but, well, that's fine. So now everything is good in that library, so it's awesome, right? We can test static assert. But there is a C++ standard core language issue with the number 15 581, which I stumbled across on Monday this week. And that is, among other things, about this. So you have code that looks quite innocent. You have, again, this basically this wrong template that we've seen before, so a value that's pretty much always false. Then you have a const expert template function with a declared return type. In the body, we fire the static assert, and then we use decal type on the function call. Okay. With MSVC and GCC, this code compiles just fine, because decal type is an unevaluated context, and as such, the body isn't even instantiated. Just the compiler just looks at the declaration of the function, and that's all it needs. In the case of Clang, it doesn't compile, because Clang has the understanding that if the function is const expr, then it has to instantiate the body. I don't know why. I read this this core issue, but I didn't understand the reasoning. The core issue has been there around for 4 years now. It's been discussed back and forth. There are bug reports in Clang, several of them. They were closed by Richard Smith and then reopened because they're really not sure what's going on. But regardless of what the outcome is, the reality is that current versions of Clang just don't compile this. Right? So everything I've shown so far suddenly breaks apart as soon as your function is const expr. That is bad. And as I saw this on Monday, I was close to saying, okay, I'm not going to give this talk because it's bullshit. Okay, but okay. So yeah, we cannot do this anymore if the function is const expr. So what now? Any ideas? Just curious. Okay. Okay, that's yeah. I think you have to be in the mood for this for a long time. So again, for the earlier slide, what do we have to do? Well, we need to test the condition of the static assert, and then we need to verify that the static assert is actually inside the function somehow. And if you look at the test, you will see what we're looking really just at the return type. Okay, we don't really test the static assert itself. We're doing an indirect test. Okay, and if we just look at the return type, that means well, we can cheat. We can just turn off the static assert for the test. Okay, so you can do something like this. This is one version of doing that. That's the preprocessor hammer that you can use on this. You just have some preprocessor variable that is set to false by default. But if you use it in your tests and set it to true, then the check for the static assert will not be false anymore. It will be true. Okay, with this code. So you can just turn off the static assert for all the rep static asserts that you define this way, and then you're good and can test again. Okay. Okay. And yes, that's what I'm doing in the live code now.
That way you test the presence of the static assert, but not the message.
So. I test the presence of this particular type, and I'm defining these types that are just shown this rep static assert with a macro. So they are bound together, and there's very little that can go wrong for that. But yes, I mean, if you want to make sure that the message is definitely correct, then I think there is no other way than testing with the build system. And you have to do that for some tests just to make sure that you don't have some systematic problem in the whole code. Okay? So you have to do some build system tests, but the bulk of the tests can be done just by checking that the return type is what is expected. Okay? Good. So that was the present. That's all stuff that you can do with C++ 11 or 14. I'm currently working on a new version of SQL++ 11 with C++ 17. That has one feature that is very, very cool for this. It's const expr_if. It's most likely going to be in C++ 17. And they can forget about all the tag dispatch. You can write everything into one function. You can have this check again, like before, and then just use if const expr on the value of the check, which is true if everything is good, and then the compiler will just compile the code that is in the if block, and otherwise it will do the else block. So you don't have to branch into functions. Everything is closer together, so it's much nicer. And it's very, very expressive. So you see directly what you want to do. And if you ignore the const expr, it doesn't even look like you're doing compile time programming. It even looks like normal runtime programming. It's very, very nice. So I love this style, and I'm really looking forward to using that. And just to give you an idea of how this will look like in real code. So I need it, and for several reasons, I need a few more layers of these types. I don't have these failure types directly in use. I need to wrap them a bit, but the idea is the same. So I have a succeeded type that, well, is basically just the std true type. I have a failed template that is pretty much always the false type. And I have a bad statement that in the standard implementation, as it is in the header file where it's defined, doesn't even work at all. So whenever you try to construct that one, it will fail with something that you don't want to use. And then there is a macro that I use to actually construct those failure return types. So it takes a name and the message, then constructs the type that you use as an indicator for the static assert, and then you wrap that into a specialization of bad statement, and then again the constructor of bad statement will explode in your face whenever you call the constructor. Okay, and there's a yes. The question is why we have a reference to wrong in there. We'll get to that in a second. But just wanted to mention that that's why it's red. So we use wrong here because, as I said, wrong is always false from the perspective of the user. We can use specializations of wrong, though, during our tests, so that we can turn off specific static asserts. Okay. What you see here is we have this empty struct with the name of the whole thing, of the static assert, that is used in the specialization of bad statement. And instead of using this ugly preprocessor nonsense that I showed before, which is easy to use but not very nice, we can use a specialization of wrong and actually set that to true. Okay, we can do that. We can do that for the tests, right? Yeah, this doesn't use the preprocessor stuff other than writing this macro. And we can see the usage of this wrong in a few slides. There, I hope it will become obvious. So then we just define some of the failure types. So for the from function, there is a test that is just helpful for users because you could call the from function with joins. If you forget the condition of the join, then it's a conditionless join and likely an error, so we don't want to have that. That is tested. It also tests whether the thing that you have is a table, and it tests whether the table that you provide to the join doesn't depend on other tables. What could happen if you have a subselect? Okay, a subselect can depend on outer things that mustn't happen for subselects that are used as tables. Then the check for multiple static asserts is very, very simple in C++17. So instead of writing some nested conditional T or whatever, you can just chain const expr if several times, check the conditions, return the failure type, or if everything is okay, you can just return the succeeded. And then, well, we now can write our function, the from clause in a statement. It takes one argument now, which is the table. It checks this argument with the check from arg function that we've just seen. Uses the value of this check to go in either of the if branches. In the good branch, it does something and returns a new statement type. That's just detail. But in the bad case, it returns now a bad statement, which, if we ever get there, will fire. Okay. Okay. So now we can test that. And for testing, what I said a few slides before, we now write specializations and set wrong, the value of wrong to true. Just for test. If you do this in code that you want to use in production, I mean, it's your problem, but for testing, that's awesome. Okay? Because now you can turn off specific static asserts. So even if some other unexpected static assert would fire maybe, and then you will see that. Right? If your test code would run into something unexpected, you could see this because you just turn off those things that you're actually interested in testing. Okay, and then the tests are very simple. You just do static assert. It's now more in the more modern version, probably in line with what Louis Dion is going to say in the keynote today. It's now testing with more values and functions, and well, it's testing if the result that you get from a call to from is this is a bad statement with this indicator struct. Okay, this assert arg is table, for instance, or assert from arg is not conditionless join. If that is the specialization of bad statement that is returned, then this static assert will be happy. If you have non-const expr calls, you can do something that's very similar. You could just have a helper function that acts on the types and basically does the same. Okay. All right. So in summary, if you want to do stuff like that, and if you're interested in yielding short and concise error messages, the first part, I think, is you have to clean up. So with tag dispatch or const expr if, depending on which version of the standard you're using, you have to use these failure return types for the bad case to be sure that you just yield that message that you're interested in. Then you can split up the static assert. the conditional static assert into an unconditional static assert in the condition. And then use the conditional type for tag dispatch or in the context for if. And you can also use it as the failure type itself, or wrap it as I've shown in SQL ++17. And then you can just write straightforward tests using static assert to test static assert. Right? And as mentioned before, for your question, yes, you have to sprinkle in a few tests that actually use the compiler and see that you get the messages that you're really expecting, just to make sure that, that you don't have these systematic errors where maybe by accident the wrong is suddenly true in all cases or something like that. Okay. All right. And have fun with that. Cool. Any questions? Thank you.
Have you released this also as a separate library, or do you plan to release it as a separate library, or is it only available in this SQL PP11 code base currently?
You mean the tools for
the
using
testing
static
framework
assert?
with the macro and all the templates already defined?
That is currently just only in, that's just currently just only in SQL +11 or 17. But it's currently one header file. It's FreeBSD licensed, so you can use it whenever you want.
Okay, thanks.
Anyone else? Thanks for your speech.
All right. Thank you.